video, I'm going to go over the first few questions from the Chapter 6 examples packet. I have a separate video that goes over all the questions for number 4, which is what I'm going to focus on in our class for the 2 days on Chapter 6. But this is a good video to watch that goes through kind of how shifting your data by adding or subtracting a number to all the data values, or taking the data values and multiplying or dividing all of them by a number, how that's going to affect your statistics. All right, and you will be for sure asked at least one question on the AP exam and the multiple choice about how your measures of center and measures of spread will be affected. Okay, so I'm going to do that in number 1 first. All right, so we've got a 40-point quiz, and we give us a bunch of information about the statistics here. We have a mean score of 30. The median is 32. IQR is 8, standard deviation of 6, minimum score was 12, the first quartile score was 27, and you got a 35. Nice job. Okay, so it says the first decision made by the teacher was to, instead of making it a 40, they're going to make it out of 50, and they're going to add 10 points to every score. So that would be like taking your data value and adding 10. So the mean's going to go up by 10, the median's going to go up by 10. Now, here's the thing that you need to know. When you take your data values and add or subtract a constant to them, your measures of spread are going to remain the same. So my IQR is actually going to stay 8, right? Because if my quartile 1 and quartile 3 both move up 10 units, doesn't matter, because when I subtract them, I still get the same difference. Standard deviation is still going to be the same. There's still the same amount of spread around that mean, even though the mean has changed. The minimum will go up by 10. The first quartile will go up by 10, and our score will go up by 10. All right, so that's the first scenario. The second one is that they're going to go back to the original and weight it out of 80. All right, so taking all of our data values and doubling them. All right, so for measures of center, those are going to double. So our new mean is 60. Our new median is 64. Now, here's the thing. Since we're multiplying all of our data values by a constant, the measures of spread will also change. So the IQR would be 16, the standard deviation would be 12. So that's the thing you need to know, the difference between the first scenario and this scenario. The minimum is also going to double, 24, quartile 1 is doubled, and our score is double. All right, now the last one, and this is the kind of scenario you would definitely see on the AP exam. All right, so they're going to double the scores and then add 20. So double the scores and then add 20. So this is the kind of the tricky part. The doubling of the scores, right, that 2 times all the data values will affect everything. But the adding of 20 will only affect measures of center. It's not going to affect the measures of spread, right? So in this one, right, our mean will go up 20 from the last column. Same with our median. But our IQR and standard deviation, our measures of spread, will just get that doubling, right? So they're actually going to stay the same as the previous one, where you only double the scores. The minimum is going to go up that extra 20. Same with the first quartile, and same with our score. All right, so kind of the takeaway from number 1 is to make sure you understand that whenever you add or subtract a constant to all your data values, only measures of center will change. The measures of spread will remain unchanged. And if you multiply your data values by a constant or divide, right, then that's going to change everything, measures of center and measures of spread. Okay, let's talk about number 2. All right, this type of problem is something that happens all the time, obviously, in the Olympics with these different events, or just in world championships if you watch anything like that. But the idea here is this is getting us to start thinking about how we can standardize these different values so that even though they're from different events, and if you look, the 100-meter dash is measured in time, the shot put and the long jump are measured in distance, right, in feet and even inches. Even if we have completely different events, completely different units, we can still kind of crown a winner or award a winner because we can do something called standardization. All right, so whenever you hear your teacher or anyone talk about standardizing, that's talking about z-scores. All right, and because we're talking about real data, I'm doing air quotes on real, or just made up problem, but real data, if you will, we're going to use this formula, y minus y bar over s. All right, now if you wanted to, as I said before, you can use x minus x bar over s. That's fine by me. It's your choice. But what I'm going to do is I'm going to standardize all of these values for each of these competitors for all 3 events. And then I'm going to use that information to essentially decide who gets the gold, the silver, and the bronze. And then ask that last question, who had the most remarkable performance in one of these events. All right, so I'm going to start with competitor A over here. All right, and I'm going to do the 100-meter dash first. So this is the 100-meter dash. All right, and so competitor A ran a 10.1 second 100-meter dash minus the mean of 10 over the standard deviation of 0.2. So I'm going to get a z-score there. All right, you can probably do this mentally. All right, but if you need the calculator, you can. When you subtract, you get 0.1 over 0.2, which is a z-score of, I'm going to do it in decimals, of 0.5. All right, we'll do the same thing for the shot put. All right, so the competitor A put the shot 66 feet minus the mean of 60 feet over 3 feet. So when I subtract that, I get 6 divided by 3, which is 2. You'll notice I don't have any units when I do these z-scores, right? The idea is that the units, and I'm using air quotes there, it's not really units, but whenever you calculate a z-score, that's telling you how many standard deviations away from the mean your actual data value was. So the farther away you are, like a positive, this case positive 2 compared to 0.5, right? The person's shot put, right, that distance is more unique than their 100-meter dash time. Let's do the last one, the long jump. We've got 26 feet minus 26 feet, so that's going to be a z-score of 0. And what I'm going to do here, because the standard deviation was given in inches, so I'm going to do all of this in feet and do half of a foot here. All right, 6 inches is half a foot. So if I do 0 over 0.5, I get a z-score of 0. Okay, so I'm going to do the same process for my other 2 competitors. So we got 9.9 minus 10 over 0.2. So this will be a negative 0.5. Then the shot put for competitor B, they actually put the shot at the exact average. So just like the long jump for competitor A, their z-score will be 0. And then for the long jump for competitor B, they had 27 feet minus 26 feet over half a foot. So that's 1 divided by 0.5, which is going to be 2 for the z-score. And finally, competitor C, 10.3 over that 0.2. So that's going to be 3 halves or 1.5. And then 63 feet for the shot put. So 3 divided by 3 is 1. And finally, the last z-score for this long jump is we've got 3 twelfths, which is going to be 1/4. So I'm going to do 27.25 feet minus 26 feet all over 0.5 feet. So this one is going to be 1.25 times 2, which is 2.5. All right, now here's the kind of the trick that when we do this, when I've done this in class with other students, is they won't pick up on, because what they want to do right now is to take all these z-scores and just kind of add from left to right to see who gets the gold, the silver, and the bronze. But you got to be careful here, because one of these events, the 100-meter dash, right, you actually want to have a negative z-score, right? You want to be faster than the mean. All right, so in this case, we want to run this 100 meters below the average, as opposed to like the shot put and the long jump, where you want to put the shot or you want to jump past what the average is. So what I tell students is, before I go ahead and find who my winners are going to be, or my winner, I take all of these z-scores in the 100-meter dash, and I just think of them as the opposite, right? Because if you think about this, right, competitor A ran slower than the mean, so they should not be rewarded for that. So I need to take away half of a z-score, if you will. And same thing here, competitor B was the only one to run faster than the average, so they should be rewarded for that. And then finally, competitor C was the slowest. So now if I were to add the numbers from left to right, competitor A is going to have 2 minus 0.5, which is 1.5 for their z-scores. And then this competitor B is going to have 2.5 And then competitor C is going to have 2. All right, so when I think about who gets the gold, who gets the silver, who gets the bronze, my competitor B is going to get the gold, competitor C is going to get the silver, and then competitor A gets the bronze, right? Because I'm just going by who had overall the best performances after I standardized them. Now, the last question said, who had the most remarkable performance of the competition? And in this case, I'm looking at who had the z-score that's farthest away from 0, right? If you have a z-score of 0, that means that for your event, whatever you're talking about, you did exactly what the mean was. So that's not remarkable at all. It's actually the least remarkable. I don't want to say least remarkable. I want to say it's exactly what the average was. So when I look at these options here, I see a couple that are in the 2s, but then I look at this one right here, which had a 2.5, right? That one is the farthest away from 0. So competitor C, their long jump distance was the most remarkable performance of this entire competition. All right. Anyway, we'll get more practice with that. As I said, we're going to focus on number 4 and questions like that in class. But I just want to show you the difference between using this type of equation where we're talking about real data, again, air quotes, real data, as opposed to what we'll focus on in class. All right. Let's do 3 and 4, and 3, these 2, and then we'll be done. So essentially what I want you guys to get used to in these 2 problems is sketching a normal model. So again, this is the shift that we're going from number 2 to number 3. In number 2, we had air quotes real data, but now we're talking about a model, right? So this is just what we expect to happen going forward. So a normal model, you use a capital N, and then you always have what we call 2 parameters. This is the mean, and this is the standard deviation. All right, so the idea being that you should always have these 2 parameters. I use the symbols mu and sigma because we're talking about a model. You'll notice in my work on the previous problem, I used y bar and s for the mean and standard deviation because that was not a model. That was coming from real data. All right, so for this model, I have a mu, maybe I'll help your brain kind of look at this, a mu of 7.6 pounds and a sigma or a standard deviation of 1.3 pounds. And this is for birth weights. All right, so we're saying that the mean for this model is 7.6 pounds. All right, and because we're talking about the 68, 95, 99.7 rule, which I'll go over after we finish drawing the sketch, I'm going to be moving 3 standard deviations to the right and 3 standard deviations to the left. Okay, so I'm just going to take my calculator and add 1.3 3 different times. So this is 8.9, 10.2, and finally 11.5. Go the other direction, so subtract 1.3. 5, and last one, 3.7. Okay, so now let me give you this in terms of the context of the 68, 95, 99.7 rule. And those are all percentages. So here's how I'm going to write the statement. So according to the model, I expect 68% of all babies born to weigh between, and this is where we're going to use the 1 standard deviation to the left and to the right of the mean. So between 6.3 and 8.9 pounds. I expect 95% of babies born to weigh between 5 and 10.2 pounds. And then finally, I expect 99.7%. So when you read that, you should be thinking almost all, right? 99.7% of babies born to weigh between 3.7 and 11.5 pounds. Okay, so kind of to summarize for you, right? give you kind of an example, right? I've had 4 children, and Ms. Byrne will be disappointed I don't remember all of the exact weights of our children, but all of our babies except for Liam, which is interesting because Liam is for sure the smallest child so far. But Liam weighed the most. He weighed 8 pounds. So if I had to draw where Liam was in this model, he'd be just to the right of the center, right? 8 is just a little bit past 7.6, but not all the way to 8.9. So Liam very much falls within 1 standard deviation above or below. All of my other children were 7 pounds and roughly 12 ounces, 10 ounces, 11 ounces. So they would be pretty close to the average as well. All right. But let's say you or your sibling or your cousin or someone you know was born weighing 12 pounds, right? See how 12 is to the right of 11.5. So we would consider that baby's weight to be unusual, all right, because they're so far to the right. Or let's say you have yourself or, again, your cousin, friend, someone who weighed only 3 pounds when they came out. We have lots of babies that are currently born premature that weigh very little amount, right? 3 pounds. I've heard for sure, I've had kids in my class that were born many weeks early that would be considered unusual in terms of their birth weight. So what we're just saying with this 68, 95, 99.7 rule is that this is what I expect to happen. Will there be baby weights that are not within 3.7 and 11.5 pounds? Absolutely. But according to this model, I'm expecting, I'm not really expecting many babies to be outside of those values. Okay, so that's where the 68, 95, 99.7 rule kind of happens. Okay, let's do the same process, but with ACT scores. All right, so I'm going to go a little bit quicker here since it's the same thing, just with a different context of a problem. All right, so 21.2 is my center, my mean. I'm moving 3 standard deviations above and 3 standard deviations below. So I'm going to take my mean of 21.2 and add 4.4 to it 3 different times. There we go, 25.6, 30, and 34.4. I'll go the other way. $16.8, 12.4, and 8. All right. Now, once I have this, again, I know we don't do the ACT anymore. We used to do the ACT or focus on the ACT at the school. Now we've shifted to the SAT. But just so you know, the max for the ACT is a 36. All right, so even a student who gets a 35 or a 36, you'll notice, is actually considered unusual, right? They are more than 3 standard deviations away from the mean on the high side. And if you get below an 8, your score would be considered unusual on the low side. But I'm going to write, according to this model, all right, using my 68, 95, 99.7 rule, I expect 68% of ACT scores to fall between 16.8 and 25.6. I expect 95% of ACT scores to fall between 12.4 and 30. And then finally, I expect, and this is where I would say, almost all, but 99.7% of ACT scores to fall between 8 and 34.4. All right, so again, it's a little more difficult to do this since we don't really do the ACT anymore, but in the past, my students could actually think about their score and see where they kind of fit in terms of this model. All right, so that summarizes kind of everything that I want you to think about so far. In class, when we go to number 4, when you watch the number 4 video, you get a chance to see how we can use this information to calculate the likelihood or the percentages of seeing values above or below with our model. All right, so again, don't forget to try the IXL links and do those exit tickets. Good luck.